Okay, welcome back. Come on down, Johnny. I hope everyone got all refreshed and you struggled through that program. Now we're on to the next thing. The last one. You made it to last quarter. Time to win the game or whatever. Okay, yes. So now we've made these Cartesian topologies, we've made derived types, we've made graph topologies. What are they useful for? So the hope is over these next 3 slides, we're going to do a brief collectives on neighborhoods, basically like 2 functions, and then we're going to jump right back into another hands-on, which will take hopefully 30 minutes, 20 minutes. We'll see, and then we'll touch on metis at the last bit of the tutorial session. So, okay. All right, so as I was alluding to, we would like to communicate with our neighbors. So the whole point of constructing these virtual topologies is to take advantage of the connectivity information of your problem, right? And so in order to do that, you can make simpler calls, right? So if I have a derived type and I know the pattern, I can use, less MPI sends or receives or collective function calls, okay? So they can actually help simplify. You put in the legwork up front to construct these things, but later on when you actually need to do complicated communications, like a neighbor, as we saw with that Poisson problem, right? We needed to talk to all of our neighbors, north, south, east, west, but can we just do it in one single call, for example? And at the same time, we might want to do collective communications, a single on this topology. Okay, so recall, you guys remember your basic collectives of all gather, right? And so on the right, we have, what does the all gather do? It says, okay, great, I want to have 1 send a piece of information to all the ranks that's involved. And then at the same time, we want to have rank 2 send its piece of information. And finally, rank 3, there we go, send its information, right? And so after this all gather operation, we wanted to perform this communication. Now, the interesting part about this is with this endowed information inside of this virtual topology, we can now do this with our nearest neighbors instead of everyone in the communicator, right? So that's where we can start to see the power once we've constructed these virtual topologies. We're just going to do a nearest neighbors that we constructed in the graph or the Cartesian to do this communication. So that's what's awesome about this, okay? So this one was an all gather. At the very top, you can kind of see where I have little special things, which is I, neighbor, all gather. That'd be the non-blocking version of this, right? So you could send your message, and instead of waiting around and be like, when is this thing gonna finish? I could be getting stuff done. You can stick an I in front for non-blocking. Then you'll get a ticket back, and you say, okay, great. You're gonna go, press my shirt or something with this data, and then I'll go do something. And then I'm like, okay, great. Let me check. I'm ready to use that data. Is it done, right? Or did I receive the data, for example? And I'll have a status ticket. And then I check the status and with a MPI wait, and then we're like, great, I can continue with my calculation, right? And then there's even more with this all gather. So here in this simple example, we're sending 1 piece of information in the illustration, right? 1 piece to each. In the top right, we see this V or W. So V is for a vector. I forget what the W is, but a vector 1 means you're going to send variable information, and John Kaz is going to tell us what the W version does. Different types. Oh, and then you have all the byte set. Yes, correct. And then you have all the byte offsets and all that fun stuff that we learned up front. It all comes back to haunt you. Okay, the other one is an all-to-all. So this, I always kind of think of a matrix transpose across the MPI ranks. So each has 3 pieces of information. It's kind of hard. There's a solid, square, hollow, square, and a triangle. And what does this do? It sends a local piece to each rank, and then, so it's basically kind of like a transpose operation in this illustration. But so again, a similar it's a neighborhood collective using the virtual topology that you provided. So you have to pass in either a Cartesian one, or you have to pass in a graph topology in order to use these. Okay? And then it's smart enough to check inside of that handle you made your new communicator that, hey, can I actually do this operation? Otherwise, you'll probably get an error. Okay? All right, let's look at an example. So we have a Cartesian virtual topology with all periodic nodes, for example. And then we'll look at node 0. And so node 0 wants to send a piece of information. And how many neighbors does it have? How many neighbors? Shout it out. 4, right? Cartesian in this example, right? So the dimension is 2, so it means we have 4 neighbors. East, west, north, south, like all of our examples, right? And so the ordering, as we could see, the west is in the x dimension on the -1 from lexicographic ordering. So when we do this communication, when I'm going to receive, so in my receive buffer on 0, right? So on 0, I'm going to send my piece of information over to ranks 2. I'm going to send this up to 6, over to 1, and finally out to 3. I probably have that built into the animation shortly. But at the same time, think I need to receive the data from my neighbors, right? I need to receive the information. So with this, because it's lexicographic ordering for Cartesian topologies, that means number 2, the x negative, is going to be stuffed into the first buffer position. Next, we go to x plus, gets put into the second slot. Let me clear this off because it gets really confusing. And then y minus, y plus. And then, of course, we see that we're sending our information out. And then they have the same principle of who's east, west, north, south, the lexicographic ordering. And it's the same picture on their rings, okay? Now, I guess I hid one of the slides. With graphs, you can do the exact same collective functions, right, calls, but the ordering and way how they get stuffed into these buffers, right, is how you constructed the graph, right, how we actually listed them when we actually built it. And so that's the expected order of the communication too. So it all kind of plays back on itself. So you know you made the graph the way it is, and you get the expected behavior. Okay, so again, another hands-on, number 4, back to basically that Cartesian one. But now we're going to replace the communications using an MPI non-blocking all-to-all with vectors. So we have some crazy types. Okay. So let me switch over to the other slide deck. There we go. That was number 2. Ignore that one. Okay, number 4. So we had our big Cartesian grid partitioning. This is just an illustration again, right? If this was split up by 3 by 3. And we made our Cartesian topology, and then we're going to send our neighbors, right? So in green, right, on this side, we're going to send this information over to this rank, right? At the same time, we will receive this set of cells from this neighbor, right? Now, why do we have the all-to-all V, the vector version? Well, if you recall, we dissolved this away in our grid, and it's because Oh, there's here, right? This was by bx, right? So it's variable data that's going to be sent within these. So you have to specify how much data you're going to be sending to each neighbor. So the west and east is going to get how much data? West and east neighbors get how much data? by? Well, yes. The general in the code, right, you'll see by. And then for the north and south, we'll be receiving and sending bx amount of data, right? Now, if we look back at that picture of, okay, we had, on the Cartesian topology where we had to pack the bytes into positions. Now, what does that look like on our, say, send buffer, right? So we're going to send this. Maybe I should have made the receive buffer. Say it's this receive, okay? So the west, right, negative x direction, we're going to send in this example, the first 6 get packed into that one, right? And then east gets packed in the next one, north, and south. Now, in these calls, you have to tell the counts. So how much data are we sending in each, right? So we know it's west, east, north, south. Well, that is the task you'll have to figure out, right? You'll have to figure out what these entries are inside the code. So hint, right? So west, how much data are you sending? We kind of talked about it. And then lastly, you'll have to fill out this displacements vector. And what are those values? That is basically the offsets. So west starts at which address? Well, it's going to start at the beginning of S buffer, right? Because it gets put in the first slot. Then you have to tell me the offsets of when all of the east data starts. And hint, hint, that little thing that went brrr, has a count on there. How many was that, in a sense? Right? And then we see for north, what's the offset starting from SBUF address out to where that purple line is. Okay, and then finally south, right? So those are the indexes from your starting address, right? We only care about the starting address and what the map looks like. Okay? I wrote 15 minutes, but we'll see how long it takes. The fun part's coming soon. Okay, you may begin. Okay, so we spent a good chunk of time on that. I want to give you one last opportunity to actually partition a graph, right? So let's look at metas, even though it directly doesn't have MPI calls, but the good thing is when we're learning those scan things with the compressed storage row scheme, CSRs, that is what you're going to need to do metas partitioning. And so we'll look at a quick example, or we'll go little slides again. And then I wrote a few programs, which the hands-on demo, you won't actually have to program anything. You guys can run the code. It'll output the actual partition meshes into a VTK format. And then if you don't know yet, you can take that data and we'll use it if you attend the visualization with ParaView. But the cool thing is this program, it'll take an unstructured airfoil, right? If you're going to do a computational fluids, which all triangles unstructured. And then you can tell Metis, like, hey, I want to partition this into like 6 MPI ranks instead of 2. And you guys can play with it and see how it works. So we can take a look at the source code and how we actually constructed it. Okay? All right. Okay. Graph partitioning, right? So these are the 2 examples, right? So on the left, we'll see we have like this triangle thing, which makes a box, and we'll partition up into crazy stuff. So the colors represent a new MPI rank, in a sense. So how do we actually do this? I guess there's multiple libraries to do graph partitioning, but one of the main ones is from the University of Minnesota. So in the slides, you can go to their webpage. It's pretty basic. And you can download Metis, or you can just, from the examples, I already packed it into the repository. And I wrote the make script, and it'll build it. And then you can lift the make file, which will link your program against this library, and then you can use it through the API systems, right? But what does Metis give you? Okay, it has a bunch of programs. So in the middle, there is standalone programs. So if you want to partition a graph, if you want, you could dump your graph to a file in their expected format and pass it into their standalone program called GP Metis, right? Graph partition Metis, makes sense? And then it'll write out to a file how you should assign each one of your nodes in your graph to a rank. So you get a vector out. And it says, okay, nodes 0 through 5 are assigned to rank 0, for example, and then et cetera. Okay? So you can partition random graphs. You can do unstructured meshes. Like this one, these are unstructured meshes, like the right one for an airfoil. Totally irregular, and how does it do it, right? Then I guess you can do even crazy compute, fill, reducing, ordering of a sparse matrix. Read the documentation. And then lastly, you could take a mesh and actually convert it into a graph itself, right? So you can dump out files, send it into their programs, but that's kind of a pain. The typical way to do this is you use their library, right, as just like if you're going to do matrix multiply, you're going to load up BLAS or LAPACK and link against their library and call their functions through their API routines. So in these, right, if we want to partition a graph, we can do, there's a couple algorithms they have built in. So like the first one is part graph recursive. So there's a specific algorithm that will actually cluster chunks of each graph into like subgraphs. And then it'll do partitioning at the low level and then propagate up. It's kind of a crazy fun thing. You guys can look at it. I don't want to go into those details too much. But so with this, here, for example, is what the function will look like. It's pretty crazy. So like first one is like num vertices, right? If we're going to partition a graph, and then there's a whole bunch of inputs. But we won't focus on the details too much. You can see which ones you can pass in as null, so you can ignore it. There's options. There's tons of things. But at the end, you get this output. So we called it part. And that's a partition vector. So for like this graph, right, we have 10 nodes. Then a part is going to store basically the rank ID. So here, purple, I guess I should have put like zeros. It's an index into the rank. I mislabeled them, right? So it'd be like 0, 0, 0. So these all should have been like 0, 0, 0, 0. It's for rank ID 0. And then 1, 1, 1. And then 2, 2, 2. Okay? Yeah, mislabeled it. Apologies, right? But that's what it's going to output. And then you're like, okay, great. I know how my graph is partitioned. Then you can jam these things into all of your virtual topologies, right? Because you're supposed to give the partition to MPI. And so this is that final piece that brings it all back together. Now, in this thing, the hard parts are this thing called X adjacency and adjacency. And we talked about this CSR format, and this is exactly what that is. So let's briefly look at an example of how that is constructed. And once you know how to do that, then the world is your oyster. Okay? The other input here, this is n parts. This is you requesting, hey, I want to partition this graph using, I want 3 MPI ranks, if you can do it. Or you put in whatever number you want. So for example, in the hands-on exercises, This is an input argument on the command line to say how many ranks are we going to try to partition this airfoil mesh, right? So this is where all the power comes from. Any questions so far? Yep. You can do adaptive, actually. So you should be careful, right, in the sense this is generic or flexible. And so this one in particular is just metis. There's also parallel metis. So if your original mesh is massive, does not fit on a single node, for example, you can pass chunks again, just like our distributed graphs, and then it'll do partitioning there. But there are special, I think, functions, right? Like they are aware of people trying to do dynamic AMR, for example, right? Changing the graph on the fly. But yeah, it's an API call. You can call as much as you want inside of a loop. But is it performant? That's another question. It's pretty good, but caveats. Yes? So, when you'll see on the next slide, like this, it is generic, right? Inside, like, but the way you input the mesh, right? You could be consistent in a sense, it's a generic graph. But it'll recognize that I want to put things that are likely together, right? It's not going to do like cyclic. That's the whole point of this. But as what's funny, right, if we look back at this example, this one, it did really weird things, didn't it? So it may not be as expected because it really works on graphs rather than, oh, I know this is a Cartesian thing and it's perfect for this. So that was part of it. And that's because it's using like this, in a sense, what's called like a multi-grid algorithm. Multi-grid algorithm is a solution acceleration technique for linear algebra problems, A equals B. Anyways, but the idea is you start with the fine mesh, and then you're like, okay, let's group chunks of 4 together, and then do the partition on that one. And what is that going to do? It's going to make even coarser and chunk all those together, and then build up from a coarser mesh to distribute. So it's like making sub-problems that are simpler to solve for partitioning, and then to get the final answer. Okay? But that's why you get these really, you can get some bizarre looking things, but in general, right, you'll see that like rank 1 is contiguous, and it tries to, somewhat optimize things, but can be sometimes not perfect. There's also iterative approaches on how many attempts you want to smooth things out, actually. So like on this one, I think I don't know if I set it up with the options. You can actually tell it, hey, I'd like you to make a more regular, refined shape. So these are really weird where it's stuck a triangle off. But if you let it iterate inside of Metis, it could make more sensible partitions. But it costs more, right? So there's trade-offs. Performance trade-offs, right? But maybe if you're doing this one time up front, you're willing to take that cost, and great. Okay, so let's look at an example of that X adjacency, which is like an indexing thing, and then the actual adjacency thing. So X adj here in yellow is going to be the size of num vertices plus 1. So here we have 0 through 14. So that means we have 15 plus 1, which is size 16. Right? So there's this size is 16. And then the adjacency matrix is going to be 2 times the number of edges. Okay, now what does this look like? This looks like voodoo magic for a minute, but I hope the animations will actually help you figure this out. Bam! What in the heck is that thing? Huh? That's what I said. Okay, now, if you ever get confused, pull open these slides and be like, oh yeah, that instructor made this awesome visualization to help me understand this, okay? So, X adjacency. You start with node index 0, right? So let's look actually at the adjacency matrix first, okay? Node 0 is connected to nodes 5 and 1. Here, I guess we'll list 1 and 5, okay? So we pack those in. So node 0 is connected to nodes 1 and 5. Put that into my adjacency matrix. The X at adjacency is basically the index of where this started. And it started in 0, so I write 0 into X adjacency. Okay. Next. Okay. Again, now we look at node 1, right, from my labeling. Who is it connected to? It's connected to 0, 2, and 6. So I'm packing 0, 2, and 6. Now, where did it start? It started at index 2. So I put the index into that spot for the, right, index 1, right, node 1. Next, do you see the pattern? So 2 talks to 1, 3, and 7. Pack it in there, 1, 3, 7. Where did it start? It started at index 5, so I put index 5 into the index buffer edges, right? Make sense? Same idea. 3 is connected to 2, 4, 8, starts at 8. 4 is connected to 3 and 9, starts at 11. 0, 6, 10 starts at 13, index 13. See it? So this is actually the fundamental mechanisms of compressed row storage. So now if you guys go write sparse matrix algebra, you can do it. But I'm not going to ask you to. So, okay. And it continues. You loop through all of the nodes in your graph, right? So that's why you end up getting 2 times the number of edges, because all the edges are doubly accounted for, right? Do you remember, like, for example, this edge on 5 said it was connected to 6, but at the same time, we can see this edge is again marked. So that's why it's 2 times the number of edges in the graph. And then the X adjacency, we're going to visit every single one of these nodes, but we need to know +1 for the last one. Where does it start? Cool? So that's basically it. And again, we're going to basically same thing. We can also partition what's called a mesh dual. Well, what's a mesh dual? So if you ever seen like Voronoi meshing and stuff. So you have a mesh, you plot out all the centroids. So ignore the boundaries kind of, right? So all these centers, so a centroid of a triangle. Average weight, if you balance it, you know, on a pen, where's that point? And then you connect them all together. And so from here, this thing in white is called the dual mesh. And if you look at algorithms and Voronoi mesh techniques, they actually just plot all the white stuff, and it looks like fancy partitioning or fancy element types. But it's really under the hood, there's actually like triangles and stuff. That's it. Okay, so last demo, you guys have survived, hopefully. We're going to do part mesh dual. I did not make this. All you guys have to do is make it and run it. Okay? So on this one, I'll open that up. So here's the thing. Inside of exercise 5, there's a couple steps. Okay? The first thing you have to do is build the metis library, which is already packed in there, and I already wrote the script. Build metis.sh. Just run what's in the yellow. Yes? Question?
So how does this metis conditioning work? Like how does it actually decide how big is the
So you're going to inform, right? Like you're going to inform what the graph looks like. And in the examples, you guys will look at how I actually count and build all the graph with an unstructured thing, right? Now, the question you're asking is, how do they actually decide who gets a plot, like what rank number? Is that the question you're asking?
So,
Yes.
how, you know,
The algorithm itself. Yeah. So, partially. They actually apply, I think, like a PDE scheme, like that Poisson equation. You can actually apply for like, I think it's like the iconical equation or something for like distances. But it looks kind of like a Poisson equation. So they actually apply a physics problem to a graph. And there's some weird underlying principle that falls out. But I think what they kind of, you should read the manual, okay? But they basically have, you know, if you had a fine mesh, they apply, I think, a physics problem or something on it. And then what they do is they coarsen it. So they'll collect, you know, these subset and then solve the problem here. And then once it gets down to basically a simple base case, we're like, okay, great. Let's do 1, 2, 3, and 4 ranking. And then who does this belong to? And so they are, oh, by association in the graph, those are also of that rank. Right? It's like a coarsening and a refinement thing. So they learn, that's how they, as far as I know, like kind of, sort of. Okay. All right. Did you guys all build Metis? Did it work? Right? Hopefully. Okay. There's 2 examples here. If you guys really want, you can go to the box one. But let's skip to the fun one. Okay. So in demo2.mesh, if you go in to that one and you type make, it's going to build it. And then you can run this program called Metis demo, and it'll take optional arguments. If you just run it with this, it's going to give you this box thing, and it's going to like partition it, I think, on like 2 or 4 ranks by default. But if you want to do a airfoil, you put like mesh ID is 2. I think there's instructions that list it. So like 2, and then you could just say how many parts I want. So like, oh, it's partitioned for like 7 ranks, and see what it does. Okay? When you run it, it's going to output a file that has like something .nparts8.vtu. So VTU is a file format from what's called VTK format. And a lot of the visualization programs like ParaView, as you'll see either today or tomorrow, Thursday, can load a VTU file. So a VTU file is, it's called an unstructured VTK file, and it knows how to handle like unstructured triangles or quads or anything like that, okay? So maybe what I'll do is I'll run this on my laptop, and I'll pull it open on one of the visualizations, and we can actually see how it got partitioned. So let's do that, and then we can look at the source code and how, like, you could literally lift it for your research. So even though I'm using like a structured, I'm reading in a mesh file, which will have like triangle, like it first had coordinates of all the points, and then it has for each element, has who it's connected to for those nodes, and then how I feed that into building a big structure, right, the adjacency matrices that we went through that fun compressed row storage, and then passed it into Metis. Now, this thing works on any crazy thing. So if you're not even doing, you know, like mesh stuff, it works on like crazy graphs. And you just put the connections in, build the adjacency matrices, feed it in, and it's going to spit out these partition vectors. And the nodes, right? So when you said, oh, this is node 1 or element 1, in the first index of the part vector, it's going to give you the rank ID number that you should assign to that node. And then you can visualize it, for example. Okay? So this should blindly apply if you have any like graph-related problems. Okay? Any questions? No? Okay, I think we're essentially wrapped up. Congratulations, you've made it through the MPI thing. Thank you for suffering through my first formal year of trying to put these together. What I really beg and ask is if we could get you guys to like do feedback. I think a part of like the evaluation program, I really would like appreciate feedback on like how I can improve this for future, right? So make notes. What you didn't like most, right? What you did like, all that is really appreciated. So thank you very much. I hope you have a great rest of the week learning high performance computing stuff. You can go learn about parallel file I/O, I think on Wednesday from John, if you really feel so engaged to learn about those derived data types with subarrays. This afternoon, that are containers, right? So 2 parallel sessions, but thank you very much.